Hi, in this video we will learn other properties of definite integral which mainly focus on the limits of the integral, upper limit, lower limit. Well, let us assume that f is an integrable function on the interval AB. And well, first thing here is that so far with the limits we were putting usually were different numbers, but if we put the same number, upper limit and lower limit are the same things, this is going to be equal to 0. Well, one way to see why this is a good idea to have such integral equal to 0 is this, that when you have a function, doesn't matter, positive, negative, wherever, you know that the integral is somehow signed limit, and if you start from a point A and go up to point A, the region formed by under or between the graph of the function and x-axis from A to A has no area. So the area is 0. The second property is that while so far we have been assuming that the upper limit is always bigger than lower limit. But now this is kind of a convention. We will allow to have upper limit smaller than lower limit. In other words, we are not going to put any condition on those ones, and switching the limits always will introduce a negative factor. So switch the limits, you get a negative sign, and done. And the third property, which is very important property, is that if you have a function and you're integrating from A to B. Let me sketch a graph here. So this is a function. I'm going to make it nice such that it's just positive, continuous, and you go from A to B. So here the meaning of the integral is area, but you can break the interval in two pieces. Pick any point between and you find first the area of the region under the graph from A to C. This area is going to be A to C of f of x dx. And while you do go the other piece, it's going to be integral of from C to B of f of x dx. If you add these two, it will give you the same result as you integrated from A to B f of x dx. In other words, you can always separate one integral into two pieces or even more if the upper limit of one appears in the lower limit of the other one. So you integrate first from A to C and then from C to B. Add these guys, the result will be the same thing as you integrate from the beginning A to the end B. Okay, so these properties are what we have to know, and let's just do some examples for this. Okay, so let me put this up there. Yes. Well, specifically, this last example is useful when you have a function defined on using different formulas, so piecewise defined functions. Well, see how this works is nice. Here you see this is constant. I can take it out But absolute value of x minus 1 is what? If x is bigger than equal to 1, this guy is going to be positive, so the result would be just itself, x minus 1. If x is less than 1, inside absolute value we are going to have negative numbers, so we have to multiply this by a negative sign, which is 1 minus x. Now we can separate this in two pieces. From 0, so there's a 3 there, from 0 to 1 of absolute value of x minus 1 dx, plus from 1 to 2 absolute value of x minus 1 dx. And why is that so again? Because you see on 0, 1 up to 1, we have one formula for the function, so we can have 1 minus x dx. For the other one, we have another formula, which is this one, x minus 1 dx. And well, just go ahead and write these different pieces now. 0, 1, 1 dx minus 3 integral of x dx plus 3, 1 to 2x dx plus, oh, there's minus 3 integral of 1 dx. And each one you can compute separately. Here, for example, this guy is the 3 times area of from 0 to 1 of constant function 1, which is a square. Oops. Minus 3. And this is the area of triangle from this to the, well, this is from 0 to 1, yes. So this is half of that square. Then 3 times area of, now you have this trapezoid, or differences of two triangles, and minus, oh, what did happen there? Okay, minus 3 times, well, again, this goes from 1 to 2, and that is another square. So the values here, this is going to be 3 times 1 minus 3 times half of 1 times 1 plus 3 times, well, you see there's a big triangle, small triangle. This will be the area of big triangle minus the area of small triangle, minus 3 times this, oops, area of that circle, that square there, sorry. Yeah. And if you compute these numbers, like this is 3, this is 3 over 2, this guy here is going to be what? 3 over 2 times 9 over 2 minus 3, all will go to 6 over 2, which is equal to. For this one, well, this is obviously a piecewise defined function, and again, for this piecewise defined function, it's better to separate the domain of integration into pieces on which we have only one formula. Well, before I do that, I noticed that the upper interval is less than lower interval, so I can switch those. This way I have a regular integral, and I can go from -3 up to -1 of f of x, and this minus sign is multiplied, and then go from -1 up to 1 here, what we have here. And this is what? Now, we are going from -3 to -1 of greatest integer x dx plus, minus from -1 to 1 of sine x dx. Very nice. When you look at this guy, well, the greatest integer, we can sketch the graph of greatest integer there. And it goes from -3 to -1. So at here it is like this. Then we have like that and like this. And what we have here is that, well, you see there is a rectangle there. There's another rectangle there. Both of them are below the x-axis, so we have to subtract it. So minus area of the bigger one, which is 1 times 3, minus the other one is 1 times 2, minus the other one is integral of sine x from -1 to 1. So if I just sketch that, something like that, and from -1 it's somewhere here up to 1. Again, I don't know what are the regions, the area of each region, but by the symmetries of sine, I know that these are the same thing. It means that I will have, first of all, this is positive part, this is negative, so the area of R1, let me call it R1, minus area of R2, this is R2. But these are the same thing, so if you subtract them, you will get 0 for this piece, and here we will get -3 minus 2, which will give us in total 5. So piecewise defined, you separate it on the intervals for which we have a single formula, and then try to use the tools we have to evaluate the function. Okay, so let's do another example here. Write the given terms as one integral, not an integral, one integral. Well, here you see I go from 1 to 2 minus. To be able to apply this rule, what is important is that I go from A to C upper bound, and then plus from the same thing up there, I start and go to another thing. But when you look at this guy here, what you notice is that, well, it goes from 1 to 2, but instead of addition, you have minus. And the second integral doesn't start from 2, it starts from 3. Well, let's, since 2 is up there, switch that one. So I'm writing the first integral. The second integral, I can switch the bounds or limits, and that way I will introduce a extra negative factor. And if you look at that guy, 1 to 2 f of x dx plus integral of 2 to 3 f of x dx. Now, the upper limit is equal to lower limit, and there's addition. So this implies that 1 to 3 of f of x dx. Okay. How about this one? Okay, see, I have to start from somewhere, yes? So here I can see that I go from 0 to 1, add, and then I start from the same one. So these two first one will give me 0 to 4 of gx dx minus integral of -1 4 gx dx. So ended to 4, it is not addition here, and it is not the same thing. So we first switch these two, you get 0 to 4 gx dx minus of 4 negative 1 gx dx. And then from there, you see that now this will turn to plus 0 to 4, 4 to negative 1, so it was 0 to negative 1 gx dx. Just one integral. How about this one? Okay, again, this is good. The first one is 1 to 2, add, and then the second one starts with 2, so this will be 1 to 3 f of x dx minus, I flip that one, 3 to 1 f of x dx, and this gives us 1 to 3 f of x dx plus 3 to 1 f of x dx, and together it will be 1. So you see, up from 1 to 3, 3 to 1, so it will be from 1 to 1 f of x dx, but integral of any function from 1 to 1 is equal to 0. So this is what we have for this kind of properties regarding the integral limits. You have to be able to work with these ones, specifically this last property.